Okay, in this video, we're going to discuss dependent RWs and also Levy flights is also a type of RW. So dependent RWs, it's a huge category of RWs, okay? When each step is dependent on one or more of the previous steps, then this RW can be considered as a dependent RW. So according to this definition, correlated RWs, they are one type of dependent RWs, right? So other very common dependent RWs include lazy walks, which means that there is probability in each time period the walk remains in its current location, which means that the walker is lazy, and sometimes with a probability, it will simply refuses to move for the next tick. Okay, that's called lazy walks. And the next one is called reinforced walks. Probability of making a particular step is greater if the link between two lattice sites has been crossed previously, or if the site has been visited before. It means that in reinforced walks, it's more likely to visit a place that the walker has visited before. And self-avoiding walks is the opposite side of reinforced walks, forbidden from returning to any previously visited location or excluded from approaching within some specific distance of any previously visited location, which means that if a place has been visited, you can forbid the walker to visit it again, or even make this rule more strict. Okay, you cannot go back to that location and a specific area, a specific distance. You use a distance to make sure that the walker cannot get even close to that location that has been visited. For example, a specific cell has been visited. You can set a buffer distance of 2 cells, say that. Then use that location as a center, okay? An area defined by a distance of 2 cells from that cell cannot be visited by that walker, self-avoiding, okay? Okay, so next, I want to introduce Levy flights. RWs with walks with non-finite step length variance, which means that when you choose the step length for the walk, you use a heavy tail distribution like this. Cauchy distribution. What's the feature of a heavy tail distribution? The tails are pretty long, right? Left tail, right tail, they're pretty long. What's the actual meaning of these long tails in terms of random walk? It means that although the probability is low, it's possible to have a very long distance for a specific step, okay? Because according to these tails, I mean, the tails, they are very close to the x-axis, which means the probability of picking a very large value is pretty low because the tail is very close to x-axis, right? Close to a probability of 0, but it's not equal to 0. It's likely, and the value, the step length could be very long. Okay, but for most steps, they still have relatively shorter step length. Okay, so that's the feature of Levy flights, right? You can use Cauchy distribution, and here is another distribution. It's called Pareto distribution. Pareto distribution. And what's the spatial pattern? What's the spatial pattern of of a Levy flat random walk. Here is the result. We can see there are a lot of segments here, and most of these segments, they are convoluted, which means that there are a lot of small steps happening within this space. And that's the reason why we have small clusters of segments and they're convoluted. But besides that, we have several relatively, I would say, relatively less long segments. And this long segment, for example, this one, it's a pretty long one. And here we have another long one. They are pretty long steps. This is what I mentioned before, with a very small probability for a specific step, its length could be very long. But since the probability is pretty low, we do not have a lot of long segments in this space. Most segments, or you can say most steps, each step produces a small segment, right? Most segments, most steps, they are pretty short. Okay, so this is the spatial distribution, spatial pattern of Levy flights. What does it mean? It means that for a Levy flight random walk, most steps, they are short. But a limited number of steps, they are extremely long. And here, let's just compare Levy flats with correlated random walk. On the left side, we have seen this figure before. It's a figure, it's a plot between t and distance. And all these gray lines, they are for the curves for correlated random walk. But on the right side, we have the curves for Levy flats. 100 Levy flats with a Cauchy distribution step length. Okay, so you can say here we have the linear curve, which is a straight line, right? Straight line between t and distance. That's the square root of t. This is for simple random walk. And you can say this solid black line is the expected change of distance by time if you are simulating Levy flights random walk. So you can say it's well above the linear movement. It means that Levy flats, they have higher efficiency. They have I should say this: if a walker is following a Levy flat, then its efficiency is even higher than linear movement, which means that within the same time, it is expected to go further using Levy flat than linear movement. Okay, that's the reason why that we have a solid black line right above linear movement. With the same time t, a Levy flat walker is expected to move longer or further than a linear movement walker. Okay, and all those gray curves, they're also simulation results. It's natural, some of them they failed, right? They failed. Their efficiency is even lower than the linear movement, even lower than a simple random walk. But most of them, they are moving with higher efficiency than linear movement. And we can say there are a lot of jumps within a specific step. There is a huge jump of distance. Why? Those are steps with extremely long length, but the probability is pretty low. That's the reason why we only have limited number of huge jumps. But when the huge jump happens, it's a huge one. When a jump happens, it's a huge one. Okay, that's where the long tails kicks in. That's where the long tails kick in. Okay. And since we're talking about Levy flat, I want to let you know that if a walker is walking following Levy flats, its behavior is called super diffusive. What does it mean? Super diffusive behavior is based on the definition of normal diffusion. So movement as a sum of small independent increments. That's called normal diffusion. Simple random walk is following normal diffusion. Brownian motion or pure random movement is following normal diffusion. Diffusion is linear with respect to time. What does it mean? The lower dashed line is for simple random walk, right? So you expect that when the time increases, the distance also increases linearly. It's very similar to a pure linear movement. This is normal diffusion behavior. But obviously, some movements, they have higher efficiency than normal diffusion. Some of them, they have lower efficiency than normal distribution. So subdiffusion, slower than normal. Super diffusion, faster than normal. So Levy flats is super diffusive behavior, right? You can also compare them. The solid black line here is the expectation, is the expect of hours for Levy flats. Obviously, it is very well above this simple RW curve. The efficiency is higher. But even for Levy flats, some simulations show that they fail to be super diffusive. They're sub-diffusive because some gray lines, they are even lower than this dash line for simple random walk. But that's just some outliers, right? So Levy flats is having higher efficiency of moving than linear movement. So it's called super diffusive. Super diffusive. And also there is another property, another feature for Levy flats. It is following power law, step length distribution. What is power law? A relative change in one quantity results in a proportional relative change in the other quantity, independent of the initial size of those quantities. So roughly speaking, a distribution with a few big things and a lot of small things. This is exactly what Levy flats is trying to show us, right? There are a lot of small steps with a limited number of limited number of big steps, right? So Levy flats, a few low probability big leaps and a lot of highly probability small moves. And if we're using a mathematical formula to address this idea of this power law idea, the probability of distance, I should be more accurate. The probability of the length of a step is positively correlated to what? To d to the power of negative mu, where d is the step length and mu is somewhere between 1 and 3. Okay, p represents pattern or p represents probability, right? And here, the important part is a specific value of mu. If mu is equal to 1, d to the power of negative 1 is actually the reciprocal of d. But no matter what, because the power is negative, d is always on the denominator, which means usually, in general, the larger the d, the smaller the p, right? Because d is on the denominator. It makes sense. The larger or the longer the step length, the less likely it is going to happen. But what's the influence of mu here? I'm going to show you. So here, let's just assume at the very beginning, mu is only 1. So here we have d, we have p. P here, I would just directly say that pd equals d to the power of minus mu, because to be more accurate, it should be positively correlated to d to the power of minus mu. But let's just draw a equal symbol here, okay? So if the d is 2, which is a shorter distance, right? And mu is 1. What's the value of PD? Is 0.5, right? Because d is 2, mu is 1. P should be equal to the reciprocal of d, because the power is minus 1, right? So the probability of having a step with a step length of 2 is 0.5, when mu is equal to 1. So if we change d from 2 to 4, which is a longer step length, the probability is 0.25. It's lower. It makes sense, right? So the longer the distance, the less likely it will be chosen. Okay, the idea is this. But let's change mu from 1 to 2. So here we're using the same independent variable and the same function here, right? This time, if d is equal to 2, the probability is 0.25. But if d is also, again, 4, the probability is much lower, 0.06. If you change mu to 3, you can say that what's the probability of giving value 2 to a step? 0.125. What's the probability of giving 4 to as a step length? 0.016. So if we ignore this part, from 1 to 3, for a shorter distance, d is equal to 2. D is equal to 2. If mu was equal to 1, the probability is 50%. When you change mu from 1 to 3, this is the probability for 2 right now. So the probability decreased by how many times? 0.5 divided by 0.125. By 4 times. Let's make it even clear. P decreased by 4 times. By changing after changing mu from 0 to 3. Okay, 4 times. 4 times. How about another distance? How about 4? This is a longer distance than 2. What happened to this distance? At the very beginning, it was 0.25. How about now? Now it's only 0.016. Probability decreased by almost 16 times after changing mu from 1 to 3. So you can see that it's much larger. I mean, decreased much more for this longer distance. So it's unfair for longer distance, right? So mu changed from 1 to 3. When mu was equal to 1, the probability of giving 2, of using 2 as the step length is 0.5. When mu is equal to 3, this probability decreased for 2, decreased 4 times. But for a longer distance, for a distance of 4, this probability decreased 16 times, which means the value of mu affects longer distance more than shorter distances, Okay, so this is the importance of mu. And let's get back. Here is the difference of the spatial pattern, between spatial pattern in terms of mu. When mu is equal to 1.5, I mean, it's still possible to have a very long step, right? But when mu is becoming larger and larger, you can say from 1.5 to 2.0 to 2.5, long steps, they're becoming less and less. And the extremely long step, like this one, is not likely to happen. This is what this spreadsheet is telling you. Shorter distance, 0.5. Shorter distance, 0.125 is still likely to happen. But for longer distance, it's pretty hard to survive when you change mu from a smaller value to a larger value. 0.25 to 0.016 it's even, I mean, it's almost impossible to pick it, okay? So as a result, you can say the influence of mu on the spatial pattern of Levy flights. Okay, more details can be found from this article, from this literature, and it's available at Canvas. Okay, so Levy flights as random walks, they are following power law. Power law between who and who, between distance and the probability that that distance is chosen. Okay, and this relationship is heavily impacted by mu, which is the power of distance. Okay, what's the real world meaning for Levy flights? They are pretty good for the simulation of foraging, animal foraging. Levy flights are good for searching for sparsely and randomly distributed resources. What does it mean? It means that if there is a monkey, he's in the middle of a forest with a lot of banana trees, and he is put randomly at a specific location within this forest, and he's trying to find food to survive. So what's the strategy here? I mean, you cannot simply go to a place and randomly go to another place. That's simple random walk. It's not efficient. You have to survive. You have to carry out a strategy, and Levy flights is a good strategy, which means what? You are at a random location. Firstly, you should search your surrounding, nearby environment, and say if there is banana. And you should just limit your searching radius to a specific value, which is a small value, right? Right, like this, a small circle. Search resources within this circle and use all of them. And if there is no resources, no food anymore within this circle, what should you do? You should make a huge jump to travel to another place far away from the initial location and search again. Use that radius again, search and repeat. And this is considered a pretty good strategy for animals to find food, to survive the nature. So therefore, natural selection should have led to adaptations for Levy flight foraging. I'm not saying that, and all the scientists, they are not saying that all the animals, they're strictly following Levy flights. But if they can survive, their searching strategy should be similar to Levy flights. Okay, should be very close to, not even very close, close to Levy flights. Search something nearby, and if you have finished the searching, go to another place very far away and repeat this process, repeat the searching. And it can also be used, Levy flights can also be used to simulate human activity. We have routine activities over short distances, commuting, regular shopping, dining out, going to work, say in France. These behaviors, they're all happening within maybe 10 or even 20 miles of your home. right? And they are very frequent. They are happening every day. But we also have rare activities over long distances, say every year or every several months. For example, large purchases, right? Business trips to another city on the other end of the country, vacations to even to maybe another country, right? So these are long jumps, long leaps, and they are not regular. Regularly, we do things, we go to places that are close to our home. Okay, so Levy flat is also good for human movement. Okay, but is a Levy flight a good description? Levy flights are one process describing small and big moves together, but small and big moves may be different processes, which means that, okay, Levy flights, they only gave us a spatial pattern of our movement, but they do not explain the mechanism behind long leaps and short leaps. Okay, they cannot provide the mechanism behind long leaps and short leaps. You should know that. Okay, okay. Obviously, routine activities, they are short leaps, right? Short steps. They exist because we need to survive. We need to eat, we need to work, we need to save friends. They are necessary. That's one thing. Rare activities, they are not necessarily, I mean, some of them, they are not necessary. For example, vacation, right? Of course, vacation is good, but you can still survive without vacation. So you can see the property of these two types of movements is different from each other. The first one is necessary. The second one, some of those activities, rare activities, long leaps, they might not be necessary. Okay, Levy flights can simulate these activities, no matter routine ones or rare ones. But you should know that behind these activities, their explanation could be different. Motivations of them could be different. Okay, be careful with that. Okay, I will just stop here and see you in the next video. And we're going to start section 4.3 from next video. Thank you.